our metrics
Okay, let me begin. Let me shortly recall you our last lecture. Mostly we introduced some convenient matrix notation, and I will recall what this notation is. We will work with algebras finitely generated by the set of generators, for example, Lij, where the rank of indices is from 1 to n. And we compose these generators of our algebra, these mostly non-commutative elements, some generators enumerated by a pair of indices, and we organize these generators into a square n times n matrix. And what is the object? What is a matrix? These elements belong actually, if we denote the A algebra generated by our generators, then this object belongs to the following tensor product. Namely, L is tensor Aj. So this object is the basis of usual matrix units in this finite dimensional space. And this objects are elements of our algebra A. And if you look at this definition, we can define what is a matrix multiplication of non-commutative matrices. For example, what is L square? It is just the product of this object. So Aj, Aks. This is a product in this associative algebra, and here and the summation is over all indices A, J, K, S. This is by definition the product of two copies of this matrix. And then using the properties of matrix units, A, S, K, J, we come to the conclusion that this is equal to sum over K, L, A, K, L, K, S. So we see that the matrix elements of this object is just can be constructed as a product of matrix elements of this matrix in the same way as with the usual matrices. But the only thing we should remember that we should keep the order of our object because the elements L, A, K are not non-commutative. Then we are interested in some monomials in generators. For example, we can take some elements quadratic elements and this object will be treated as the matrix element of the matrix A1, B2. Here we defined the big copy, for example, BK, where K varies from 1 till some number P, in the following way. This matrix with index K belong, this is very big matrix. And the precise structure of BK is 1 tensor so on 1, and at the case position we have matrix units. And at last B, A, J. Here we have P factors. And only one of them is not unity, but at the case position we have a matrix unit. So if you take into account this definition, we can see that contrary to the classical case, we have that A1, B2 is not equal to B2, A1. Indeed, if I calculate this object, I can see that this is a A1 J over 1 over AJ. This is A1, and then 1 tensor A KS B KS. This is B2 according to my definition. So let me continue here. The product of these matrices should be taken as an usual matrix analysis. This is AJ tensor A KS, and here I should take the multiplication of this non-commutative object from my algebra. This is precisely A1, B2. And then, if I try to calculate the product of these matrices in opposite direction, B2, A1, I'll get the same matrix notation here, the same matrix here, AJ over AKS, but here I'll get the BKS AJ. IJ. And clearly this object is not equal to this one. Only if the matrix elements belong to a commutative algebra, then these two matrices are equal to each other. If our algebra is non-commutative, it is not the case. Actually, here we have, when multiplying the non-commutative matrices, we have two kinds of multiplication. First kind is the multiplication of matrix itself, like row is multiplied by the column. And the second kind of multiplication is the multiplication of the matrix elements inside of this row and column. So clearly here we have the same matrix structure, but the matrix elements standing at the same position are different. So we have such inequality. And only if our algebra is commutative, we have A1 B2 is equal to B2 A1, and this can be considered another expression of commutativity of our algebra.
Yes, I mean, the last time we talked about this, I mentioned it was a little bit counterintuitive, because when you have tensor product, it is natural to assume that tensors which take place in different tensor legs, they commute with each other.
Yes, I tried to explain this again in slightly different way. I have already erased the definition. So this object A1 as a matrix is AJ tensor 1 tensor AJ, and B2 is equal to 1 BAJ. And these elements, as elements of endomorphisms Cn, of course, we can multiply. If I forget about this end, I can equally multiply this from the left and this from the right, and vice versa. I'll get the same answer. But I have an additional multiplication inside of this. I have a multiplication of this object at the end of my, and so in this case I will get the same matrix structure but different matrix elements at this and this at any position. Okay, and also we accept the notation that if I have a repeated number of matrix spaces, then I should take a matrix multiplication in the intermediate position in the indices of this repeated matrix space. For example, if I get element A, J, B, K, S. Pardon?
Can I ask a question?
Yes, of course.
So A1 and B2 act on defined spaces. So A1 acts on the first space and B2 acts on the second space. These elements
do not act anywhere. This is just an algebra. And the precise definition, if you take some representation, then you'll get instead of this A some operator. But now we have what we have, this some element of associative algebra, of non-commutative associative algebra. All what we can do is multiply these elements with each other. And this A1, a precise definition of this object. This is a very big square matrix where in some places I have the non-commutative elements of my algebra. This object do not act on some linear space and so on. This is a matrix, and I define in which sense I multiply these matrices with non-commutative elements. If I have an object from endomorphism of C, I can multiply the elements from for example, here I have some matrix M, and here I have some matrix element B. So the product of such elements N over A is by definition N over BA. Here is a product in my non-commutative algebra A, and here is a product if, in the algebra of endomorphisms. This is by definition. And if I take this definition, I'll immediately get this inequality if this product is non-commutative.
So, if the algebra is commutative, then A1 and B2 are commutative.
Of course, yes. If the algebra is commutative, for example, if this is a usual numerical matrix, of course, then A1 B2 is equal to B2 A1, and we get the situation as in the classical matrix analysis. But here,
So this non-commutativeness doesn't come from the non-commutativeness of matrices, but the element itself.
yes, the non-commutative generators of my algebra I organize into square table and call this table a matrix with non-commutative elements. I can multiply the matrix elements, the elements of my algebra, and then I should define what I will mean by the multiplication of a matrix with non-commutative elements. And the definition is as follows.
I understand.
Okay, okay. So if I have the product of such elements with 3 pairs of free indices, I will treat it as the matrix elements of this matrix. And if I have such a writing, I have a repeated number of the matrix space, then the monomial corresponding to the matrix elements of such a matrix is, for example, A alpha, B Ks, C alpha J. So, and the sum over alpha from 1 to... I have a matrix summation in the first space. This is a first space, this is a first space, and this is a second space. And also I'll define the permutation matrix, the matrix of permutation operator. This is a n square times n square matrix of the form AJ times JA from 1 to n. This is a permutation matrix, and this matrix just numerical. So here I can put the one of my non-commutative algebra. So this is a just numerical matrix from the point of view of this product. And then P, for example, 1, 2, A2 is equal to A1, P and 2. And the same if I put here A1. This can be easily derived from this definition. It is a very important property, and I will use it in what follows. Then, after introducing such a matrix notation, we consider the matrix, the algebra of functions on a matrix algebra. erase this because it is just repeating of the last lecture. Okay, so we considered the matrices, the complex matrices n times n, and consider the dual space, the space of linear functions, and we introduced here the coordinates of this linear function with respect to the basis dual to the basis of matrix units. And this is the coordinates here with respect to the dual basis to the matrix units. And then we considered the Poisson structure on the polynomial, on the algebra of, I consider the functions on this space. This is a space just of differentiable functions in n squared variables. Any functions of t11, t12, and so on. And I will restrict myself to the polynomial functions. It will be sufficient for me, polynomial functions. And then we defined the Poisson structure t1, t2, Poisson-Lie structure connected with a GLN algebra Lie. P1, 2, T2 minus T2, P1, 2. This is the standard Poisson structure on this space. And we have proved that that this Poisson bracket has a big center. The generator of the center is elements pk trace of p to the k's power. The functionally independent elements are p k from with k from 1 till n, because the higher powers of matrix T are dependent on the lower matrix powers due to the Cayley-Hamilton identity. This is a central elements of this Poisson structure. And then we ended our last lecture by introducing another Poisson structure, the so-called Sklenin bracket. Georgi, I'm sorry, what part of my writing I can erase? This Poisson structure is still not very complicated in the sense that we have a linear dependence of generators on the right-hand side. And then I can quantize the algebra with this Poisson structure by means of, for example, the Dirac procedure as it done, for example, in quantum mechanics.
P1 to T2 minus
P2, T2, P1, 2.
And also T2.
Yes. This is a usual Poisson-Lie structure. So when quantizing this Poisson-Lie structure, I just get the algebra GLN. I mean that here we have a commutator, T1, T2, and here I put some parameter H, P1, 2, T2 minus T2, P1, 2. And this is when H is equal to 1 due to this relation is inhomogeneous, I can always set the H is equal to 1. It is just to control my quantization procedure. And then when H goes to 0, I restore my commutative algebra. And this is just the universal enveloping algebra of GLN. here I have no problem with quantization because there is no ordering problem on the run high side. I have a linear dependence of my generators. Then let us consider another Poisson bracket, the so-called Sklyanin bracket. On the same commutative algebra. I keep this Poisson-Lie bracket, and let us consider the following expression. T1, T2 is equal to T1, T2, R12 minus R12, T1, T2. Here, R12 is n square times n square numerical matrix. And by definition, I will say that this operation is bilinear with respect to each argument here, and by definition, it satisfies the Leibniz rule. So if I have T1, T2, T3, this is an arbitrary quadratic monomial. This is a linear monomial. It's just by definition T1, T2, T3 plus T2, T1, T3, as it should be. And then let us ask ourselves, which condition should be imposed on this matrix in order this structure would be a Poisson bracket? What should we guarantee? The antisymmetry of this operation and the Jacobi identity, or Jacobi identity on this. So I should have T1, T2 should be anti or skew symmetric operation. This is the first requirement. And the second one, I should have T1, T2, T3 plus cycle 1, 2, 3, 2, 3, 2, 1 should be equal to 0. Of course, these requirements are satisfied only if the matrix R is taken in a specific way. Not for any n square times a square matrix we have such conditions. Okay, let us consider first this one. Using the properties of permutation operator,
So this is just for the sake of equability. So the only condition you have is equability, right? The only condition you have. All the other conditions hold automatically.
yes, by definition, by definition,
Leibniz rule, symmetricity, and equability, right?
no, Leibniz rule and bilinear properties are imposed by definition.
No.
So I should guarantee the antisymmetry and the Jacobi identity.
Skew symmetry is also guaranteed by definition.
No. It imposes the requirement on R. Which requirement? Let's consider this bracket. It can be written as P12, T1, T2, P12. P12 squared is equal to 1, and when this operator comes through this object, it converts it into this form. So if I substitute here my definition, then I'll get T1, T2, R21 minus R21, T2, T1. But because our coordinates are commutative, T1, T2, T1 is equal to T2, T1. So the only change is in the indices of our matrix. Here, by definition, is a matrix of such kind. So, for example, R T1 A B A J is just R12 A J A B. So, if I require that this expression is equal minus T1 T2 and compare this part and this part, I'll get that I should have a the following condition. The commutator T1 T2 with the sum should be equal to 0.
You commuted this notation, you obtained this equality, right?
Yes.
So what is the difference between the second line?
Let me.
Second line, again, from the first line.
Okay. This object is equal.
You just moved R21 because this operator, right?
Yes, I substitute instead of this Sklenin bracket that expression.
Yes, then you get this equality T2 T1 times R21 minus R21.
Yes, this is just a permutation of P with this
How
expression.
do you get the second line? This is just
Because T1, T2 is equal to T2, T1, it's commutative matrices.
right.
We have a coordinates, we have algebra function.
I forgot about them. Yeah,
Yes. So if I consider, if I look at this expression and then that one, and will require that they should be equal with minus sign, I have the first requirement on this matrix R. If I calculate, this is much more cumbersome calculation, but not very, very difficult. If I calculate this expression in explicit form, then I'll get the second requirement on the matrix R, and it will be written in the following form. And this matrix relation is called the classical Young-Baxter relation. Classical Young-Baxter relation. If I have this relation, then I guarantee that my operation satisfies the Jacobi identity. The most important requirement on the Poisson bracket. A solution of such matrix relation is called the classical Aromatics. So let me give you an example of the classical aromatics, and I will shortly explain from where we can take such aromatices, the classical aromatices. I'll consider an object of the following form. I will write this R capital. This is the so-called Drinfeld-Jimba aromatics. This is also n square on n square matrix, and in the basis of matrix units, this object has the following form. A parameter Q, which is a complex number, non-zero complex number. Then I have a sum E, I, J, diagonal matrix units plus is not equal to J. A, J, and here J. Okay. And then the last term, Q minus 1 over Q, the sum A is less than J. So the first term and the last term define the diagonal structure, and at the off-diagonal places we have just units somewhere and mostly zero everywhere. This is an object. An example when n is equal to. If n is equal to, this is a 4 by 4 matrix, and this matrix has a following form: Q 0 0 0 0. Here we have Q minus 1 over Q 1 0 0 1 0, and Q and the last position. And this difference I will often denote by lambda. This is a so-called Drinfeld-Jimba aromatics. What properties of this object? First, it satisfies the braid relation. Similarly to the usual transposition of symmetric group, namely R1, 2 multiplied R2, 3 multiplied R1, 2 is equal to R2, 3, R1, 2, R2, 3. If I put here a permutation, P1, 2, and so on, this is just the braid relation of the transposition in symmetric group. And the second one, this is a braid relation. Sometimes it is also called the quantum Young-Baxter relation, but I prefer to call this braid relation because the quantum Young-Baxter relation has a slightly different form for different matrices. And an important property of this matrix is the so-called Hecke condition. R minus Q multiplied by 1, R plus 1 over Q multiplied by 1. So the characteristic polynomial of this matrix is quadratic. And its spectrum is Q and 1 over, minus 1 over Q. An equivalent relation is and from this characteristic polynomial, we see that this matrix is invertible, and R minus 1. From this form of this characteristic polynomial, multiplying it by R minus, by inverse R matrix, we get the following simple relation. All these are equivalent, of course. And then, if Q tends to 1, as can be easily see from this explicit form, my matrix R tends to the sum AJ which is just a permutation operator, because the last term tends to 0, and the sum of these terms at this limit gives me just a permutation. And then I define a slightly different form of this aromatics, which is used in the theory of integrable models. I will denote it by this R beautiful. This is just a permutation operator multiplied by my R. And this is usually called R matrix, and this R beautiful satisfies the quantum Yang-Baxter equation. 1, 2, 1, 3, and it is this object which give me the classical R matrix, R beautiful. This is a direct consequence of the braid relation on the matrix R.
So what is lambda in this relation? You say when you wrote R squared is equal to 1 plus lambda R.
Lambda is the definition of the difference Q minus 1 over Q. By definition, this. And if Q tends to 1, this braid R matrix tends to the permutation, so the R beautiful tends to the unity. So let us introduce the parameter Q is equal to like a Planck constant. And we'll consider the limit to unity of this Q. Then the linear term in H is the classical R matrix. It can be easily obtained from this relation. If I put here such an expansion into this cubic relation, then at 0 order in H and in linear order in H, I have an identity, and in the second order of H, I get precisely the classical Yang-Baxter relation on the matrix R. So it is easy. It is easy exercise. I will not write it in explicit form. It's very easy to obtain, and I suggest you to do it by yourself. So if I multiply this by pi and make such an expansion, I'll get, for example, that lambda is equal to 2h plus R of h. And then I'll get the following form of the classical aromatics. Sum over A from I from 1 till n, y I times I plus 2. This 2 is comes from this lambda. The sum of A greater than j E I j times E j I. This is a classical aromatics, and for n is equal to, I have from here I have 1, 0, and 0, 1. This is when I is equal to 1, and this is when I is equal to 2. Here I have total 0 elements, and the only non-zero 2 is very, very degenerated matrix. This is an example of such kind. But if I have such an explicit form of the matrix R, I can verify what is R12 plus R21. I should verify that this sum commute with T1, T2. R12 plus R21 is equal just to pi 1, 2. Because R21 is just has the same diagonal term, of course. And here I'll get the following sum. And when I add this expression with that one, I'll get just a permutation operator. So this condition is evidently 0, and such a matrix will guarantee me the antisymmetry of the Poisson bracket. Here I have written only an example of the classical aromatics, which I'll obtain from the Drinfeld-Jimba aromatics. But there are a lot of matrices satisfying the Hecke condition. I mean, this quadratic polynomial has a name, Hecke condition. Not only Drinfeld-Jimba aromatics, but for example, the Kramer-Gervais Aromatics and some other, all of them are examples of Hickey-type Aromatrices.
The Hickey condition is crucial for the
Crucial. This is
non-box structure to hold.
for what?
Non-box, just wonder, what is the purpose of having the Hickey condition apart from this given some kind of
I mean the following: any matrix R satisfying this condition will produce the
this is called the Hickey condition.
yes, the Hickey condition with quadratic minimal polynomial will give us the quasi-classical aromatics of this type.
So you mean that if the R matrix, the quantum R matrix, verifies the Hickey condition, then the corresponding
The correspond obligatory this is very easy to verify because, for example, which is written here, this is written P R beautiful because R is equal P R beautiful is equal P to R and P squared is equal to 1. So I can express the Braided matrix in terms of this matrix R. Squared is equal to 1 plus lambda P R beautiful, and then expanding this R beautiful in terms of H, I'll immediately get this condition. It's very easy to verify. Okay, let me finish at this stage with the Sklenin bracket. I will also write an explicit example and say about the center of the Poisson bracket, of the Sklenin Poisson bracket. If n is equal to, then using the explicit form of R matrix, classical R matrix, and denoting the matrix elements of our matrix T in this way, I'll get the following brackets. AB is equal to AB, AC is equal to AC, AD, here we have a difference, 2 BC, and BC are Poisson commute, BD is equal to BD, and then CD is equal to CD. I do not write here the index SK, Sklenin. This is a Sklenin bracket. For n равно 2. And contrary to the Poisson list structure, the Sklenin bracket has a small center. The only central element is determinant of T belongs to center to Poisson center of Sklenin bracket. Of course, and all the polynomials in this determinant T. For example, the trace of T, let us consider the trace of T is equal A plus D. Pardon? determinant T belongs to the Poisson center of this bracket. This means that only determinant.
Only when n is equal to 2 or for any n.
For any n. It can be more or less easily proved for any n, but here we can.
So the trace doesn't commute with it, right?
Trace is not a central element. The determinant, the quadratic element AD minus BC, commute with has a zero Poisson bracket with A, B, C, D, and this one is not. For example, if you calculate with element D, yes, A plus D, we calculate the Poisson bracket with element D, and looking here, we have that this is 2BC, and D with D is 0. It's not equal to 0. The trace is not a central element, and it can be proved for arbitrary n that the only central element is determinant.
So the center is one-dimensional, right?
Not one-dimensional. It is infinite dimension. It is generated by one generator.
That means that algebraic, it has one degree of.
Yeah. Yes. Yes. So this Poisson structure allows us to consider the factor over the determinant is equal to 1, for example. But they cannot be restricted to the orbits of coadjoint action of the group GLN on the matrix algebra mat star. It can be restricted only on the group. Determinant is equal to 1. We can consider such a factor and get the group SLN. This is a Klein bracket. And the second very interesting bracket, which will be the object of my main interest, the so-called Semyonov-Tinshansky bracket. It is not.
Sorry, what is known about the center of this kind of bracket in general?
In general?
Yes, in general.
What do you mean? What is known?
I mean, the transcendence degree is always 1, or maybe bigger.
No. Algebraically, if you use two things on the matrix R, that this matrix R commute with T1, T2, it is not obligatory equal to this one. It's sufficient that R12 plus R21 commute with T1, T2, and the second one, it satisfies the classical Young-Baxter relation. If you impose these two conditions, then you automatically get that only determinant is central. It can be calculated by hand practically immediately.
The center drops, the dimension of center drops somehow. Very strange. The dimension of the symbol. So it means in particular that this construction cannot be produced from, say, Kansevich. Oh, no. There is not yet computation.
And the second time is Semyonov-Tinshansky bracket. It is not a commonly accepted name, but I prefer to call this bracket in such a way because Semyonov-Tinshansky considered such kind of bracket for the orthogonal, in quantization of orthogonal group. And it is also quadratic. It is also defined on the same algebra of functions, And it has the following more complicated form: T1, T2, STS, Семенов-Тиньшанский, is equal to R 2, 1, T1, T2 minus T1, T2, R 1, 2, and plus 2 more terms, T1, T2, R1, 2, T1 minus T1, R2, 1, T2. Here R is GLN aromatics. A classical aromatics coming from the Drinfeld-Jimbo aromatics. This is a quadratic bracket. Maybe let me write an example immediately. T is, as usual, A, B, C, D. AB STS is equal to minus 2AB. AC STS is equal to AC. AD at Poisson commute 0. BC is the most complicated element, is equal to A multiplied by D minus A.
So R12 is again a quantum classical Yang-Baxter equation.
Yes, yes. Classical aromatics coming from GLN. We have just written an explicit form of this aromatics. Then at last CD is equal to 2CA and B. And D is equal to minus 2AB. It's much more difficult to prove that this is indeed a Poisson bracket, especially it's difficult to prove that it satisfies the Jacobi identity. But the very interesting property of this bracket is that it has the Poisson center, which is the same as for Poisson-Lie bracket. Here we again have that all the traces, the elements pk, belongs to Poisson center. The center is large, is very big. And the second very interesting property of this bracket is that it's compatible with Poisson-Lie structure. I mean that if I consider the set of Poisson brackets, по-английски говорят пучок. Как сказать пучок скобок? Pencil. A Poisson pencil. If I consider a construction Z1, Z2, Z and arbitrary numbers. And I organize the following linear combination. Z1 and here the Poisson-Lie bracket plus Z2 Семенов-Тиньшанский bracket.
This is true for all n. This
Что?
is true for all n. All natural numbers n.
Here?
No, I mean for all dimensions.
or all dimensions of what?
Of the GLN.
Of course. For any n.
Not just for n equal to 2.
And then for any z1 and z2, this is a Poisson bracket.
Just wonder what kind of commutative, can you obtain commutative family from this bi-Hamiltonian structure? This is what they call
Let me say a couple of words about this slightly later. So, in order to verify that this is a Poisson bracket, of course, the main thing is to verify that it satisfies the Jacobi identity. And here we have a mix of Poisson-Lie bracket, should be calculated by the rule of Semyonov-Tinshansky bracket, and so on. And nevertheless, this will be a Poisson bracket, and of course, these brackets has the center of this one, and after quantization of this pencil, we get the so-called reflection equation algebra, modified reflection equation algebra. The mysterious thing, for me, mysterious, is that if I quantize this bracket, I will speak about this on next lecture. If I calculate, if I quantize this Poisson bracket, I'll get the quadratic homogeneous, the quadratic algebra, the so-called reflection equation algebra. It first appeared in the models, in integrable models with boundary. If I quantize this pencil, I'll get the algebra with isomorphic to the reflection equation algebra. And from this
for all Z1 and Z2,
yes,
you get the same algebra, the reflection equation algebra, right?
yes.
But just, but we will speak about commutative families generated by this pencil.
Let us postpone this discussion to the quantum case,
Okay.
but there is some interesting peculiarities of these algebras, which is connected with these Poisson structures.
Can I ask, so the whole center is generated by this case, or it's
Yes.
bigger?
It is not. I do not know the rigorous proof of this, but for the GLN Aromatics, it's more or less evident from some continuity arguments. But for arbitrary R, I do not. I can only say that these elements belong to the center. Maybe it's bigger. But for the Drinfeld-Jimba Aromatics, because it is a flat deformation of the, for example, of universal enveloping algebra, it's very plausible that the center is the same as for the universal enveloping algebra, not bigger. Okay.
And the same was before, when we consider the previous bracket, the Kleiner bracket.
Yes.
The proof that the center is generated by determinants. It is right that it is correct that it's generated by the determinant.
Yes, it is generated by determinant for GLN case. But if I consider the classical Matrices coming from the Matrices of other series, it will not be. I mean the Semyonov-Tinshansky bracket. It will not be the Poisson brackets on the linear space. I should restrict the matrices T by some additional condition to restrict it on the group. It is not defined on the whole linear space as for the GLN case. But for the Semyonov-Tenshansky bracket, at least it is a theorem which can be, which is written in the paper by Fadeev, Takhtajan, Reshetikhin about the quantization of group and algebras. Okay, maybe.
Point to stop here.
I stop here, yes.
Before we proceed
Because
to
it's so.
differential equation algebras, which will probably be the next step if you talk.
Yes. So we have finished with classical situation, and from the next lecture we come to the quantization and to the studying of the properties of quantum algebras, which appears from the quantization of these structures.
Okay. So let us thank the speaker.
And thank you for attention.
Okay. Are there any questions? Are there any questions?
А там есть кто-нибудь живой уже? Все.
Нет, там есть еще китайцы ушли.
So if there are no questions, then we just stop the broadcasting right now and see you next week, next Tuesday. Thank you for your attention.
Mm-hmm.
Так, теперь нужно отнести эту штуку в, как зовут, Миша, в учебную часть. Да, я просто хотел тебя узнать как раз насчет этих контактов.
Я как раз тебе хотел сказать. Они мне прислали только что вот ссылку на оплату. Я прям могу сейчас оплатить.
Когда
Они
нужно
тогда
будет
27 приблизительно, там 2400.
А ты послал им это уже?
Да, 2400 на двоих, то есть по 1200.
Елки-палки. Слушайте, она, эта штука, я нажимаю выключиться, она мне спрашивает, сделать мьют или офф. А я не знаю, как ей сказать офф. Я еще раз нажимаю.
Батарейки и все.
просто долго.